Hey, everybody. We're going to look at the derivative of the exponential function today. Exponentials are definitely one of the most important functions we have. The classic examples that we use them for are things like interest accruing on some kind of investment, population growth, or depreciation in value, or decay. Radioactive decay, right? So they show up in some pretty interesting places and they're very important. So obviously we want a derivative. There are some things about exponential functions that proving are beyond the scope of this series. And so we're going to assume things like they are continuous. There'll be a couple limits in here that we're going to take on numerical intuition and some ideas that we're not going to dig deep into the mechanics of. And that's fine. It's beyond the scope of this, and we want to make sure we have a derivative of these functions. So let's jump in and do that. So here is our exponential function, y equals b to the x, where b is some constant. It's got to be positive. Okay. And let's just look at the derivative of this. So we'll look at dy dx. We'll use the definition of the derivative, the limit as h goes to 0 of, so we're going to have x plus h minus b of x all over h. Okay. So now we're going to do a little bit of algebra here. So I'm going to rewrite this first term as b of x times b of h. That's just the rules of exponents, minus b to the x, sorry, not of x. And then I'm going to factor out that b to the x. And I've got b to the h minus 1 over h, okay? So now this limit is asking us what happens to this thing as h gets smaller and smaller, right? Well, this first factor in the numerator, b to the x, changing h doesn't do anything to it. X is some number, b is a number. H changing doesn't change those numbers. As far as this limit's concerned, that thing's a constant. And so we can pull that to the front. And we're left with this. We're left with this limit here, okay? Let's examine this limit a little bit. There's something very interesting happening here. If f of x equals b to the x, notice that f prime of 0, let's use our definition of the derivative at a point. We have f of 0 plus h minus f of 0 all over h is equal to the limit as h goes to 0. So b to the x, 0, f of 0 plus h, we're putting in 0 plus h for x. So we're just putting in h. So we get b to the h minus f of 0. If I put in b to the 0, we get 1 all over h. And so this limit right here, right? Notice that this thing here, this is exactly this piece right here. This limit happens to be the derivative of this function at 0. Okay. Now, we just made a couple of big assumptions. I assumed that this limit exists. Okay. I assume that this limit right here exists. It does, but showing that is not in the scope of this series. And so we're going to just assume for now that it does exist. Okay. What we end up with, our result here tells us some very interesting things. First of all, it tells us that if the derivative at 0 exists for this function, then it exists everywhere because b to the x can be evaluated for any number x. And so if the derivative at 0 exists, then the derivative exists everywhere. And I said we're going to assume that that derivative exists at 0 because we're not going to dig into proving that limit exists. Okay, so that's one thing. It also tells us that the derivative is proportional to the function itself, right? So this number, this is a number here, f prime of 0. It's some number. And so in other words, this dy dx, right, or f prime of x, if we're calling this thing f of x, is just equal to some number, I'll call it a for now, times the function itself, right? In other words, the way this function changes is proportional to the value of the function, right? That's what this is. That's one way to interpret what this is saying. And that makes sense. If we think about, let's go to one of the examples I had in the beginning of what we use exponentials for. If you invest money, let's say you're investing in something that returns 10%, right? Well, if you have $100, then the way that principle, that would be the value of the function, changes each period. What do they call that? The period of time for your interest to pay off. Let's say it's yearly, if you're getting 10% per year. If you invest 100, you get $10 per year. That would be the rate of change, $10 per year if you have $100. But if the value of your function, in other words, the value of your investment at that time is $1,000, then 10% is $100 per year. And so it's proportional to the value of the function at that point. Okay, same thing for a population. If some little microbe can double its population every hour, right? So if we have a function that tells us the population and it doubles every hour, then if the population is 10, then that population is going to increase by 10 in the next hour, right? That would be the rate of change then, 10 per hour. But now that the population is 20, in the next hour, it's going to double again. Every little microbe splits in half, and we get 20 per hour, and then 40 per hour, and then 80 per hour. So each time we get a new value of the function, in this case, the population, the rate of change is proportional to that, okay? So this is a neat feature about this function, that its derivative is related to itself in such a clear way, okay? So let's look closer at this idea now. Let's think about, I want to move. Let me try that again a little bit differently. There we go. Oh no, I don't want it to move. All right, I couldn't get that to work. So I want to look closer at this idea of this limit and this idea that our function is proportional to itself, where the constant of proportionality is the derivative at 0. So let's look at a graph here. So I've got a graph of an exponential function, right? B to the x, graphed in blue, and b is, right now, its value is 2, and I've set it up so that I can change the value. So one thing I've done is, first of all, I've looked at this limit, b to the h minus 1 over b to the h, or I've looked at that expression, and I've put in values of h. The Desmos calls it x1, but those are our h values, getting closer and closer to 0 from both the positive and negative side. And all this is doing is giving us a little bit of a sense that it seems like it is approaching a value. If you see that we're at 0.71, then 0.69, 0.69555, 0.6933 something, 0.6929. And the same thing from the other direction, right? On the negative side, we're coming in closer to 0.69 something, okay? So this is just a little bit of a hint that this limit does exist. Now, remember also what this limit represents. It represents the slope of the tangent line. F prime of 0 is the slope of the tangent line at x equals 0. So I've graphed that tangent line here when b equals 2. If I change the base of our exponential, right, I've gone up to now 3 to the x. So we started at 2 to the x, we go up to 3 to the x. We see that now that same limit, the slope of this tangent line, right? This limit represents the slope of the tangent line is 1.09-ish, right? These numbers are getting closer and closer to 1.09 something. So when the base is 2, the limit is something approaching 0.69-ish. 3, we get something a little bigger than 1, right? So somewhere between those two values, it seems reasonable to assume that this limit is approaching 1. We're starting at below 1 and we're going to something above 1. And if I can do this graphically, here's a line, this dotted gray line is the line through that 0.01. That's where they intersect the y-axis at x equals 0. Our tangent line starts out below that with a smaller slope and then gets a larger slope, right? So somewhere in there, it seems like we're passing through a base for the exponential that has a tangent line of 1, right? Right here looks pretty close to it. And it's a number, as we expect, between 2 and 3 and a little bit closer to 3. All right. Now, this is very hand wavy. This is not how mathematicians have discovered this, right? There's much more rigorous methods, but this is just to give us the idea that this seems to exist. There's some value, there's some base, the b value, for which this derivative at 0 is equal to 1, right? And if you look at the limit now, I've got something that's 0.99. If I go a little bigger, it goes above 1. I can't do any better resolution on this on the computer, but it gives us at least a guess that this might exist. And it can be proven that it does exist, that these limits exist, that we can make sense of all this, okay? So let me summarize what we just said. Somewhere between b equals 2 and b equals 3, there is a value for b such that for f of x equals b to the x, f prime of 0, which we just said is the limit as h goes to 0 of b to the h minus 1 over h, that this is equal to 1, right? There's a value between 2 and 3 such that this limit, this derivative at 0 is equal to 1. We're going to give this value a name. Name, we call it E. That's one way that we can define E. There's other ways E shows up in lots of places, but this number, we're going to call it E. Okay. The E comes from a famous German mathematician. I believe he's German, named, it looks like it should be pronounced Euler or something like that. Euler is how a lot of people say it. I think the German is closer to Euler. I think if I was German, I would say it a little. I listened to somebody online saying, and it was oil. I can't do it. But anyways, something like Euler is what a lot of people say. It's named for him because he just did a million things in math and he did a lot of things around this number. So we call this number E. In other words, if f of x equals e to the x, then f prime of 0 is equal to 1, okay? And the number E, let's give an approximation, is about 2.71, right? That's what we saw when we were trying to find this here. Right now I've got it at somewhere between 2.71 and 0.72. Right? It's an irrational number. It goes on forever, 2.71 and on and on and on and on and on. Let's see if this gives us, an approximation, right? 2.7182818286, and it just keeps going. All right, so that's the number E, right? So let's take this one step further. Oops. And by the way, this is one reason you may have heard this called the natural exponential, right? We can take 2 to the x, 5 to the x, a billion to the x. These are all exponential functions. Sometimes we call this the natural exponential. This is one hint at why we might think of this odd number, this strange number, as natural. It has this very nice property that its derivative at 0 is equal to 1. We can take it further, though, with the work we did up here. So remember, if f of x is any exponential, but in particular this one, we discovered up here that the derivative is equal to that exponential itself times its derivative at 0. But we just said the derivative at 0 for e to the x is 1. That means its derivative is only itself, okay? Let me say that one more time and write it in a different way. The derivative of e to the x is e to the x, right? Other than the trivial 0 function, right? The derivative of 0 is 0. I believe this is the only function that has this property, right? This is a pretty incredible property. It is its own derivative. The value of the function at each point tells you how the function is changing at that point, right? Other exponentials have a similar property. This still holds for all exponentials. They're proportional, but the rest of them have a constant there that we'll get to a little later. But this is a pretty big deal that we now have the derivative of the exponential. The natural exponential, e to the x, is just itself. We also just, to be clear, we sometimes write the exponential function this way, exp of x equals e to the x, right? This is just a name like sine or cosine. It's the name of the function. And the reason we do this is because it's often not e to the x. We might have something more complicated that we're putting in there, a function of x. So we'll do an example like that in just a second. Let's just do some examples with this derivative. Let's start with something relatively simple. Let's suppose I had y equals e to the 3x, okay? So I can't apply this rule directly. This rule only tells me what to do when I have e to the x. I don't have e to the x, I have e to the 3x. However, I have a way to deal with this. I have the chain rule. If I let f of x equal e to the x, move this down a little bit, and I have g of x equals 3x, then this y is equal to f of g of x. And then I know by the chain rule that y prime is f prime of g of x times g prime of x. Well, let's compute our derivatives. The derivative of e to the x we now see is just itself. G prime of x is equal to 3. So this becomes f prime, which is e to the x, except it's f prime of g of x, is going to be e to the 3x. So we have e to the 3x, and then times g prime, which in this case is just 3. And that's an uncomfortable way to write it, so I'm going to write it like this. And so now we have our derivative for this pretty simple exponential. Let's do a more complicated one. Let's suppose I have this. Y is equal to e to the x squared plus 1 over x squared minus 1. Okay, here's an example where this exponent notation is becoming a little bit tricky, and this is why one might write this as exponential, the exponential function of x squared plus 1 over x squared minus 1, right? So if we get these complicated things that can show up in our exponents, it's easier to not have to write them in that tiny little space, okay? But they're the same thing. This is the same thing, right? Well, we might want the derivative of this again. So in a similar way as before, I'm going to use the chain rule. And this time I'll stick with e to the x for my f function. And g of x is now this much more complicated function, x squared plus 1 over x squared minus 1. And again, I think I didn't give myself enough space. All right, so having written it this way, I now can see that this is the composition of f and g, and its derivative is then f prime g of x, g prime of x. So let's compute these derivatives. This is the easy one. G prime, I notice, is a quotient function. And so it might work well to use the quotient rule. So I need the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function. Got a little tight there. And then all of this over the bottom function squared. Okay. All right, so now we can go through, take derivatives. The derivative of x squared plus 1 is 2x times x squared minus 1 minus the derivative of x squared minus 1, which is 2x times x squared plus 1. And this is x squared minus 1 squared. And you can expand this, and what you'll see, we get this multiplication gives me 2x cubed. This multiplication gives me negative 2x cubed, so that disappears. This multiplication gives me minus 2x. This multiplication also gives me a minus 2x, so I end up with minus 4x all over x squared minus 1 squared. So there is g prime of x. All right, so now we're ready. Let's f prime. Remember, this is not going to be f prime of x, but f prime of g of x. So that's going to be e to the x squared plus 1 over x squared minus 1. And so we can write this whole thing then as e to the x squared plus 1 over x squared minus 1 times this negative 4x all over x squared minus 1 squared. Okay, and there we have our derivative. All right, so let's do one more thing with that derivative. So let me just write down what we have again. For y is equal to e, let's write this way, exponential of x squared plus 1 over x squared minus 1. Y prime is equal to the same thing times negative 4x over x squared minus 1 squared. Okay. Just copy what we had up above. Let's remind ourselves what this derivative does. The derivative, of course, tells us the slope of the tangent line. Let's find a tangent line for this function. Let's look at the point at the square root of 2. Well, let's write it this way, at x equals the square root of 2. Okay. All right, let's evaluate this. At x equals the square root of 2, y is equal to the exponential function. Well, square root of 2 squared is 2 plus 1. Square root of 2 squared is 2 minus 1. So it looks like we have 3 over 1 or 3. So this is just going to be e cubed. So our point is root 2 comma, oops, not 3, 3 cubed, e cubed. Let's approximate e cubed. So it's between 2 cubed and 3 cubed. So this is going to be between 8 and 27. It's closer to 3, so it's going to be closer to 3 cubed. So I don't know, 24-ish, something like that. We need the slope of the tangent line. We simply evaluate y prime. at x equals root 2. So we'll get y prime is equal to the exponential of, well, we just did this a second ago. So I'm just going to put in 3, right? Because this first part of our derivative is just the function itself. And we just computed putting square root of 2 in and got the exponential at 3. So we just need to do this part, negative 4 root 2 over x squared minus 1 squared. So that's, well, x squared, root 2 squared is 2, minus 1 is 1, 1 squared is 1. So this whole thing is all over 1. So this is a pretty ugly way to write this. Let's write this all as negative 4 root 2 e cubed. Okay, and so there is our, there is the slope of the tangent line. So putting this all together, the tangent line is going to be at x equals root 2, y minus y sub 1 equals the slope x minus x1. So in this case, we figured out that the y value of the point is e cubed. The slope is negative 4 root 2 e cubed, right? So this x minus root 2. Just want to remind us, if we get these ugly things, that's just a number, right? It's just a number. Even though it looks all pretty strange, it's just a number. All right, let's look at a graph of this. This is a pretty strange function. So let's see. Let's turn all this off. Here is this exponential function that we have graphed here, exponential of x squared plus 1 over x squared minus 1. And here is the tangent line. So at root 2, let's get a better view. So e cubed is up at 20, I guess 24. I was off by a bit. So let's change our view. Let's look at it just from negative 1 to 2. That includes root 2. And here let's go from, let's just look at it between 16 and 24. All right, so let's put in the point root 2 and e cubed. So there's our point of intersection, and we see the purple tangent line is sitting right on top of that function, right? So we see obviously the function does much different things as we go away from that point, but right there, they're pretty well matched, right? Zoom in really close, and there's almost no difference between the two of them. Okay. All right, so I think that's gonna be it for our exponential function. I'm just gonna remind us what we discovered here. This is a pretty big deal. The derivative of the exponential, a natural exponential, is equal to itself. And then of course with that, let's do one more example. Let's just combine it with, we saw it combined with a couple of chain rules here. Of course, it works with all of our rules. So if we have something like the derivative of x squared e to the x, we do our product rule, we'll get the derivative of x squared e to the x plus the derivative of e to the x times x squared. So we get 2x e to the x plus x squared e to the x. All right, and maybe we can write this a little nicer. This is going to be x e to the x times 2 plus x. Maybe that's nicer, I don't know. All right, so again, just to demonstrate, it combines with all the other rules in exactly the same way. We have a product here, we have the function x squared and e to the x, so we can use the product rule. Up above we had composition, so we use the chain rule. Okay, thanks everybody. That is going to be it for this one. I will see you next time.